a little bit of another miscommunication. So sorry about that, but I guess take it away.
Okay, thank you. So I'm going to make a sort of like review introduction on higher spins. So I'm going to say like many things, so it's hard to make it pedagogical, but it doesn't mean that you should not stop me if something is not clear. So at least at some point I will try to be pedagogical. Okay. So yeah, so let me first state what is the problem. So the problem is ultimately simple. There are such fields, you can think of such fields in, let's say, Minkowski space, which are higher speed fields. And you would like to construct their interactions. So you would like to construct theories that feature such fields which interact in a consistent manner. So this looks, and the approach that we are going to take is just study consistency conditions from the field theory perspective, so in the most general framework. So one example of such consistent theory is string theory, which is usually formulated in some different language, so using like strings, like here a form sheet. But here what we are going to do is to start from, let's say, more field theory perspective that is looking at fields one by one and trying to construct more consistent interactions. Okay? So I'm going to start from free fields. And for simplicity in 4D Minkowski space. So there is a well-known statement by Wigner that fields in 4D Minkowski space are unitary irreducible representations of the Ponomarev group. Moreover, they have been classified. Classification is very simple. So you can have fields which are massive fields and with spins 0, 1/2, 1, all the way to infinity. And also have massless fields, which are somewhat different. Also, all spins is 0 half integer. So at this point, when we are talking about representations, you can do it in a very abstract mathematical manner. So just talking about representation space, looking at each operator, how it acts on it. But usually it's not what we are used to do. We would like to look at everything as fields on Minkowski space, right? Which means that we have to look at them as functions on 4-dimensional space, and also we'd like to have the Lorentz symmetry manifest. So if we will try to write these representations in a Lorentz covariant way, we need to impose the following equations. So first of all, we need our fields are going to be rank S symmetric tensors. So this is how we know them. So index mu1, mu_s, so S symmetric indices. These are our fields. And equations of motion we have to impose to describe unitary reducible representation which is massive is as follows: Rho plus m squared. By the way, I will shortcut notations in the following way. So just one index mu and number of them in brackets. So this is a standard Klein-Gordon equation, right, that you would expect normally. Then one irreducibility condition is that it is transverse in the sense that you pick different way. So you pick one index. So essentially divergence is 0, one irreducibility condition. Another one is the trace is 0. So it turns out that these three equations together, they describe massive field of spin S. For half integer, it's a bit more complicated. I will not go into that. So the question is, what happens if, so it was m squared non-zero. So what happens if m squared is 0? We have exactly the same equations, just m taking to be 0. But it turns out that this is not enough, because the resulting representation is reducible. Yeah, so if you just do that, it turns out that this representation is reducible. And you need to quotient out some states from it which are moreover non-unitary. And that's why you need to add gauge invariance. So you declare that all like configurations of this form are pure gauge. So in this way you quotient out the states. So this is symmetric gradient. Where psi satisfies the same conditions, but with s replace s minus. Okay, this is it for Lorentz covariant form equations of motion. Okay, so from now on, I will focus only on massless fields. So there is no like fundamental reason to do only that. It's maybe just more interesting because, as I said, it's related to symmetries. So we want to discover some fundamental symmetries of nature by trying to see, to push further theories of these fields. So from now on, I'll focus only on the massless fields. So no questions about that.
Can we count components? In this case, are you going to have two s plus 1 components for the massive case and 2 components?
Yeah, so here, just one. Just two. Okay. Some unusual feature that we can see already now comparing to lower spin fields. If we look at these equations or at these, we can clearly see that they are not naturally Lagrangian, right? Because you can take your off-shell fields to be traceless by writing something like phi mu s with a wave operator inside. You can construct an action, right? It produces for this equation, but it doesn't give another one, right? So you see already, like at 3 levels, right? The action is quite tricky. And the way out, you introduce auxiliary fields. To make it Lagrangian. So in massless case, the minimal set of auxiliary fields was found by Fronsdal. So you need to take phi mu s, which is traceless. Plus take another field, let's say tau mu s minus 2, which is also traceless. And you can conveniently combine them into s, which is double traceless in the sense that you can imagine this field to be just this. So this one is a traceless component, and this one is just trace of this HBS. Right? So you have this H, and also you have gauge transformations, which are exactly the same as it was here. Okay, I'm just raising, lowering this, I think Then it turns out once you have this off-shell field and this gauge transformation, then you just start from the standard kinetic term. Then you add all possible terms that you can imagine. All other terms.
With fixed coefficients.
So you can start without fixing coefficients. You write all possible terms that you can imagine given this condition. And then you fix these coefficients by requiring that it's gauge invariant with respect to this gauge transformation. This fixes these coefficients unique, this requirement. So gauge invariance this actually fixes unique.
Sorry, what are the other two? I haven't understood.
So for example, what you can do, for example, you can write rho mu s minus 2.
Okay, so H is doubly traceless, but it still has a trace.
It has trace and also the divergences. You can take divergences.
Oh, right.
Yeah, so there are something like 5 or 6 terms in total.
So where are the auxiliary fields?
Well, by auxiliary field, I mean that one would naturally think of like natural candidate for a shell field, something which is traceless, irreducible. But since it's not traceless, it has one non-trivial trace. This one I call I use the auxiliary field.
No, wait
So
a
maybe
minute.
it's not.
On the left-hand side, that phi, was it not traceless?
So
Was it traceless?
this one is traceless.
Ah,
But I'm saying that this is not Lagrangian.
I know, but you should add it to the list then. This was not mentioned, or maybe I missed it. That's supposed to be traceless, you say. That's fine.
Yeah, this one is traceless.
Oh, yeah, I'm sorry. Yes, thank you. So, William's auxiliary fields are these towers, basically.
Yeah.
So just to make sure I understand it, so the spin 2 case, the way so this is the standard story that you take the graviton, then you've got the purely spin 2 piece, and then you've got the trace part of the graviton. And then the idea is that's just going to generalize for any other spin. You've got a spin S and a spin S minus 2.
Yeah, so for graviton you have G mu
Right.
without any conditions, right? So it's just
Right.
symmetric, it's not traceless. So you can, yeah, it indeed falls like as a particular example in this construction, but it turns out that it's not so natural to extend it to higher spins without putting any constraints. So it may seem natural that you just take, let's say, mu s, as indices without any constraints. But it turns out that
What you want is this double traceless.
yeah, you need this sort of like awkward double traceless condition that some people actually like to fight, and there are papers on trying to remove that. Okay, so this was the free theory, and now we are going to interactions.
Just one more question. I know you're going to go into any detail. I'm just curious for the half integer spin. Is it the same story that there's like one extra field that you add?
Yeah.
Okay.
So, interactions.
Now the plot thickens.
Yeah. Okay, so as we don't have like any kind of input expectation, what we are going to expect, what we are going to have, with like theories like related with some like GR, for example, it's essentially based on Riemannian geometry. Once we know Riemannian geometry, we have a lot of tools how to construct gauge invariant actions, and we don't have to do much. Here we don't have like any, let's say, geometric kind of underlying picture, and this is why we will just study all consistency conditions that come from field theory, like in full generality. And we will do that to simplify our life, just perturb it. So in this form, this means the following. As I explained, gauge invariance for massless particles was important to get rid of unwanted degrees of freedom, which were ununitary, like non-unitary and healthy, and we want to maintain that interacting that way. Which means that we start from our free theory, right? And we want to deform it with interactions. Just order by order. And what we will also do, we will deform gauge transformations. Okay, let's sketch. So let's put 0 here, which indicates that it was of zeroth order on fields H.
Sorry, I had a question from before and I didn't realize it. Why is there a divergence condition? Why
Just
did you put that?
irreducibility condition. To make it irreducible. Otherwise, it's not irreducible.
UIR, irreducible representation.
Oh, got it, sorry. You split the Maxwell equation in 2 pieces. Right, okay.
Yeah, so you
Yeah.
can see that it's consequence.
That seems hard.
Dmitry, can you put plot dot 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 in the first line? So that, okay.
Okay, and we are going to demand that delta of S equals 0, which then decomposes into delta S2 equals 0, delta 0 S3 plus delta 1 S2 equals 0. And so on. And then we are going to approach this problem order by order. So this is satisfied automatically because this is our starting point from the lecture classification. And so, like, this is the first equation to tackle. And here I would like to make, maybe I should go there, or I can just, okay. So here I would like to stress an important role of locality in all this business. So I would like just to illustrate you that if you don't take into account locality, then these equations, they don't fit any constraints. So I wrote there that delta 0 plus 3, delta 1 plus 2 equals 0. So you can rewrite this as equals h, delta 1 of h. And this piece is, so just like ignoring some minor details, it's just box H, right? It's free equations of motion. So this equation can be, it implies that delta 0 is 3 is gauge invariant on free shell. So this sign means on shell, on free shell.
So that means that under the integral sign, this is a rigorous statement. If I use the full equation of motion that I get from this action, that I will get 0 exactly if I throw away total derivative term under the integral.
Not
right?
only total derivatives, but also use that box H equals 0.
Not box H is 0, the whole equation. I mean, we have extra stuff, right? The field equation is not just box H is 0, is it?
No, yeah. So Frontal equation is more complicated. I'm just like to simplify it. But usually, on shell means using free equations of motion, which are Frontal.
And the subsidiary condition as well. Maybe that's what you mean.
Yeah.
The first list of equations you wrote for m squared 0, you wrote 3 equations, right? Box is 0,
Yeah.
divergence is 0. So what you are saying, just to make sure I understand what you're doing, in varying S2 with respect to H, I'm allowed to use those 3 equations that you have. And then I'm allowed to integrate by part. And so
Yeah,
made
yeah.
the total derivative terms. Okay.
Yeah.
Okay.
Yeah, okay, but and this is what actually people solve when they want to find vertices. But you can notice here that if delta 1 of h is itself proportional to both minus first power, then it just cancels this box. And it turns out that this condition is just empty. It doesn't produce any constraints.
Can you invert the operators that Ergen was just saying? Ergen was just pointing out that it's not really box, right? So can you actually, is there an inverse for the operators that he was pointing out? You actually.
Well, the story is similar. So like you can like put some to simplify life, some intermediate like gauge fixing to do some gauge fixing, and then it becomes essentially just box.
Maybe the subspace restricted by the condition.
Yeah. So you need to impose locality. And how you should do that? It's like a matter of choice. There is no like prescribed way. So normally we don't want to have more than 2 derivatives, right? Like in theories that we are used to, we don't have more than 2 derivatives. But one can ask that we don't have, we have finite number of derivatives. But even that, we would like to relax and require that if we have some like action of the form a and like derivative 2 to the power n, then we will ask that a n goes to 0 when n goes to infinity fast enough so that 1 over box is not produced. So this is a bit maybe like.
In Minkowski case, have people not come up with a very mathematically highbrow, precise definition of what this condition means, the locality condition? In Minkowski case, at least. Is there a
I
more
would say
rigorous
that
definition?
the best way is to compute amplitudes and to check whether they are singularities or not for associated vertices.
What's an example? Well, what's the weakest fast enough? Like, does it have to die factorially fast, or does it just exponentially, or how fast?
Well, it's something like simple from numerical analysis.
Which is?
Well, you should just ensure that.
Or I shouldn't say 1 over n factorial, that's exponential more or less, intuitively. But what if I have 1 over n times n factorial? Is that good enough?
What's
So,
1 over n times n factorial.
Well, definitely.
That's good enough?
Yeah. You should have like infinite radius of conversion. So good. These were some generalities. Let me give the outcome. If you do that, the square spins, what do you get? So if you do this analysis, it turns out that for a triplet of hairspin fields, matrix hairspin fields, S1, H, S2, H, S3, you get like list of, so okay, it's in general D, so let me first start in ABD. You have a list of vertices. And we have the number of derivatives. S1 plus S2 plus S3. S1 plus S2 minus S3. Where S3 is the smallest one. which means that if you have at least one field of spin higher than 2, you need at least 3 derivatives. So you can easily see that, let's say if you have spins 3 to 2, then this lower bound is 3 plus 2 minus 2, which is 3. So this is S1, S2, S3, and this is number of derivatives. Which is somewhat unattractive, right? That you cannot have lower derivative interactions.
That we have what?
Higher derivative, that you have higher
Well, it
derivative.
could be a lot worse, right? You should be grateful you get 3 derivatives. What more do you want?
Well,
No
people
derivative?
like to have 2 derivatives, right? Because you have like normal
Mm.
momentum, which is first derivatives of fields, and that's it. You don't need to like Ostrogowski instabilities and stuff.
Sorry, I lost track. What is these HS1s? They're really H mu S1, H mu S1?
Yeah.
It's okay,
So,
it's okay.
Yeah, just to let.
Okay, so S1, and it's really okay to have like S1 equal to S2? Like you'll have 2 fields of the same spin?
Yeah, self-interaction, like you have gravity self-interaction.
Oh, okay. And then the number of derivatives equals, what is this?
So it starts from S1 plus S2 plus S3, just sum of spins, and then goes down by 2 until it reaches S1 plus S2 minus S3, where S3 is the smallest out of space.
Are these independent vertices? All of them are okay?
Yeah, well, they
Separately?
have different number of derivatives.
Each one of them has a arbitrary coefficient in front.
Yeah.
If I want to add them
Yeah,
to the
that's
action.
Yeah, let me just give you one example.
Are you writing down like the most general figures or is it-
Yeah, this is the most general solution
With 3 fields.
with 3 fields.
And first derived by Messiah, I think.
And what is this 3 minus 2 minus 2 and all that?
So this was an example that you have spins 3 to 2, so this one is larger than 2. The number of derivatives is already 3. So, well, actually the reason why it's unattractive is that, for example, if this is S, you get S here. But this means that you cannot have like minimal coupling to gravity.
Remind us why, please.
Because minimal coupling to gravity is something like your field times stress energy tensor, which is like 2 derivatives.
Oh, I see.
So this doesn't work. And let me give you just.
You already kissed goodbye to Einstein, I see. Okay.
But in some sense, well, I will tell you that this can be circumvented. Just one example, if you have S zero. You can construct a vertex which looks like H.
Are you making a claim that these vertices all have to happen, all have to occur, or? How do you not know, why can't I just write one that has 2 derivatives in it and say that's my?
No, you cannot try to derivatives because it's inconsistent with consistency conditions in these ones.
Okay, so there's a claim that you will generate all these vertices.
No, you can. They come with at this point with independent coupling constants. So you may pick only one of them and still.
Well, whichever you pick, there's a limit on how many minimum number of derivatives and maximum derivatives. There are many possible vertices, but in each one, I mean, there's a limit on number of derivatives, max and minimum.
So if I start with 2 and then just say I have 3 fields and there are 2 derivatives, then I just get what?
Pick any of the 3
I'll get
spins.
3 in there too?
Yeah, I mean, you have a condition, where's your condition, Mitya, for the minimum number of derivatives?
So here's
And the maximum is the total, that's it. As long as you obey those conditions, you can write any vertex.
the claim is that for spin S, you will have